Hello, I will show you our approach to preventing bending and twisting effects in point cloud maps, a problem that we have been working on in the Northern Robotics Laboratory at the Laval University. I will start with two examples of the environments that motivate our work. Then, I will briefly present the gravity-constrained scan matching algorithm that we propose. Finally, I'll show the effects it has on the lidar mapping. The first type of environment we have been experimenting in are subarctic forests like this one. The forest creates a natural corridor around the trail. The drive is bumpy even in the winter. You can expect large distances, usually driven straight without any loops. If you deploy lidar mapping in this scenario, you can expect drift. I'll show you a point cloud map being built by this mobile robot along a 1.5 kilometer long forest trail. As the point cloud map is being incrementally built, there is drift both in the position and orientation. Here, the red map is constructed by the standard Iterative Closest Point algorithm, minimizing the point-to-plane error metric. You can see this bending downwards. This deformation has multiplicative effect on the final error, and in our case, it is around 60 meters in elevation. We face a similar problem in the underground environment with long, uniform corridors and tunnels. We have experienced this kind of environment in the DARPA Subterranean challenge. It has been shown in the literature that there is a systematic error in lidar mapping in tunnels caused by the fact that the laser beam is in fact a cone, not an ideal line. The drift then depends on the robot's distance from the tunnel walls. In the example shown here, the standard solution drawn in white is bending downwards, similarly to the forest experiment. While mobile robots usually carry some sort of an inertial measurement unit, we propose to exploit this sensor to suppress the drift in the roll and pitch angles. In the scan matching problem presented here, the white lidar scan is about to be matched against the point cloud map. Since the robot carries an IMU, the input can be correctly oriented in the pitch and roll angles. Then, the matching algorithm only needs to find the translation and the rotation around the vertical axis. In the paper, we derive a point-to-plane error minimizer that does this. The solution has already been implemented in the libpointmatcher library, and you can test it yourself. In the example from the forest trail, we prevent the map deformation in the roll and pitch angles, reducing the vertical drift. In this case, towards the end, our solution stays within a few meters from the reference position provided by an RTK GPS. In comparison, the standard solution accumulated those 55 meters in the vertical drift. I will use the opportunity here to present one more experiment. The robot was teleoperated on a trail around the lake. The distance was more than 3 kilometers this time. This trajectory allows us to compare the starting and the final point. I'll show the output of two mappers in parallel. The red map comes from the standard point-to-plane ICP. Our approach produces the blue map. The video has been accelerated because the experiment took 1 hour to record. Also, please note that only the relevant parts of the map are shown, as the mapper tries to save the system resources. You can see that the standard solution in red is gradually drifting downwards relative to the blue map. This part of map, this section, is usually the most difficult to map since you observe only the road and trees in a long corridor-like geometry. As we will approach the end, we will see that there has been some mapping drift as the starting and finishing points are not overlapping. Let's look at the whole final map. We have accumulated some drift in the horizontal plane but both approaches show a similar result. The difference is mainly in the elevation. The standard approach drifted downwards by almost 70 meters, while we have drifted upwards by 20 meters. I have presented our modification to the ICP algorithm. It is a simple modification, but effective in suppressing the drift. We consider it to be a useful tool in your SLAM toolbox, potentially helping with the subsequent loop closures and optimization. It is available online in the libpointmatcher library. The question left for the future work is how to extend this gravity constraint to other types of ICP error metrics, and how to provide an automatic calibration of the relative pose between the IMU and lidar. Thank you for your attention.